This is a lesson about the concept of power. In our study of energy and changes in energy, we haven't really discussed anything about how long it takes to change energy. Or, if something is doing work, we haven't talked about how long it takes to do the work. For example, if I have a bookshelf and a 50 kilogram or maybe 120 pound box of books sitting on the floor, and I want to move those books 2 meters up to the top shelf of the bookcase, then it doesn't matter if I pick up the entire box of books and place it on the shelf and it takes me 5 seconds, or if I take each book one at a time and place it on the top shelf and it takes me 5 minutes. In both cases, I've done the same amount of work, and I've changed the energy of the books by the same amount, even though clearly it's harder to move the books all at once in 5 seconds than it is to move them one at a time in 5 minutes. So that's what the concept of power is designed to address, is this idea of that it's important to be, how fast are you doing the work? So power, in the physics sense of the word, is equal to the work that you do divided by the time that it takes you to do it. Or, equivalently, how much you are changing an object's energy divided by the time that it takes you to do it. So that you can see in the case of moving these books, if it takes me 5 seconds, then I'm going to be dividing by a small t. So I would have a large power. But if it takes me 5 minutes, then I would be dividing by a large t, and my power would be less. The unit of power would be the unit of energy or work, which is the joule, divided by the energy, or the unit of time, which is the second. Okay, and the joule per second occurs quite often in physics, so we do give it a special name. It is the watt. The abbreviation is a capital W, and the full word is W-A-T-T. And that's the same wattage that you're familiar with in the context of electricity, and we'll talk about that a little bit more in a little bit. Okay, so to do a quick example, how much power is it going to take us to move these 50 kilogram, how much power are we using if we move the 50 kilogram box of books 2 meters up in 5 seconds? Well, first, I need to figure out how much am I changing the energy of the box. So if we say that the potential energy of the books is 0 down here, then the change in energy of the books is just its potential energy on the top shelf, which would be equal to mgh. That's 50 kilograms times 9.8 meters per second squared times the change in height, which is 2 meters. Okay, if you round the 9.8 off to 10, then that would be 1,000 joules. Okay, so this is approximately 1,000 joules. So if it takes me 5 seconds to pick the box up and put it up there all at once, then the power is 1,000 joules divided by 5 seconds. That would be equal to 200 watts. On the other hand, if I lift up each book one at a time and it takes me 5 minutes, then the power would be 1,000 joules over 5 minutes, but I need to change that time into the standard unit of time, which is the second. Okay, so we'll we'll multiply by 1 minute over 60 seconds. That way the minutes cancel, and I end up with joules per second, or watts again, except this time it will be 1,000 divided by 5 divided by 60. And that is 3.3. Repeating, so that's about 3.3 watts. So both people, the person who does it in 5 seconds and the person who does it in 5 minutes, change the energy of the books by the same amount, and therefore are doing the same amount of work, at least in the physics sense. But the person who does it quickly is using 200 watts of power, while the person who does it slowly only is outputting 3.3 watts of power. Okay, well, as I said before, you can, this is the same watt, the same unit that shows up in electrical appliances. So when, for example, you buy a 100 watt light bulb, then it means that that light bulb uses 100 joules for each second that it's on. So let's do an example illustrating how electrical power is no different than any of these other kinds of energy or power that we've been talking about. So I'm going to clear this. Pause if you're not ready to erase. Let's figure out, so if we have a 100 watt light bulb, and it's on for 10 hours a day, okay, then let's find the energy that it uses in 1 month, or 30 days. Okay. Well, this time we know the power and the time, and we're looking for the energy. So we still use the equation, power is equal to energy divided by time, but we're looking for energy this time, and we know power and time. So let's multiply both sides of this equation by the time. We get power times time equals the energy used by the light bulb. Okay. The power is 100 watts. The time is 10 hours per day times 30 days. That would be 300 hours. But I need to convert that into seconds if we're going to get an answer in standard units. So we have 3,600 seconds in 1 hour. Okay, so now my hours cancel. And that gives us the change in energy of our light bulb. How much energy did our light bulb use in that month? Okay, so you need to get a calculator to multiply all those numbers together. We have 100 times 300 hours times 3,600 seconds in an hour. And that gives us 1.08 times 10 to the 8 joules. That's how much energy one 100-watt light bulb uses if it's on 10 hours a day for 30 days. Now, that's a big number, 108 million joules. And that's just one light bulb. So if you're a homeowner and you've got 10 or 20 lights that you're using, and you also have a washing machine and a heat pump and who knows what else that's using electrical energy, then when you get your electric bill at the end of the month and you're a typical consumer, then you may be using billions of joules. So since the typical consumer doesn't understand scientific notation, then you'd be getting a bill with a whole bunch of zeros on it if you're using 10 billion joules of energy a month. So the joule is not really a very convenient unit of energy for the power company to use when billing consumers. Instead, they use a unit of energy called the kilowatt hour. Now, the kilowatt hour, if you just glance at it, you might think that's a unit of power because it's got the word watt in it. But actually, it's a unit of energy. Look what happens. See, when I take this equation up here, the power equation, and I multiply both sides by time, then you see that if you have a power times a time, then you end up with energy. And that's what we have down here. A kilowatt is, in fact, a power. But hour is a time. So this is a unit of energy, not a unit of power. And it's a much more convenient unit of energy for the power company to use. Let's figure out how much energy our light bulb is using in kilowatt hours instead of in joules. Okay, well, 100 watts, I need to convert that to kilowatts. So you have 1 kilowatt is 1,000 watts. And then I need to multiply by the number of hours that the light bulb is on. Well, that's easy, 300 hours. We already figured that out, 10 hours a day times 30 days. So that's 300 hours. And that's it. 100 watts divided by 1,000 watts per kilowatt times 300 hours. So that gives you 30. 30 kilowatt hours is the amount of energy that our light bulb uses in a month. Now that's a much more convenient unit. If you get a bill for 30 kilowatt hours, that's not nearly as confusing as for 108 million joules. So if you're curious, you can look on your electric bill and see how many kilowatt hours you are using every month. And you can also look and see what the electric company is charging you for each kilowatt hour. Now, depending on exactly what power company you use, in Kentucky it's pretty cheap. It's going to be somewhere around 8 cents a kilowatt hour, maybe up to 10 cents a kilowatt hour, depending on exactly where in Kentucky you live. If you live somewhere else, California, it's going to be 4 to 5 times that at least. And in some places like Hawaii, it may be 10 times that. But our rate in Kentucky is about 10 cents or $0.1 per kilowatt hour, meaning that it would cost us $3 a month for that light bulb. Now, $3 doesn't sound like much, but if you talk about per year, then, well, that's $36. And if you have 10 lights instead of just one, well, now we're talking about $360. So if you could save on your electric bill by increasing the efficiency of your lights, you might actually save $200 a year or more. And it's not that hard to do. You can get a 23-watt light bulb that puts out the same amount of light as your 100-watt light bulb, but uses 75% less electricity. So if you replace your light bulb with a high-efficiency one, then you might actually save $150 or $200 a year if you do that with each of your light bulbs.